Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the weld joints. And in this particular presentation, we will be talking about the failure of the dissimilar steel weld joints. So, to understand the failure of the dissimilar steel weld joints, it is important to understand what are the difficulties imposed when a dissimilar steel weld joint is made using the fusion welding process, and what are the various strategies to reduce the issues related to the dissimilar metal welding or dissimilar metal joining. Okay. So, considering this content of this presentation includes like fundamentals of dissimilar metal joining, where we will be talking about the what are important factors related to the dissimilar metal joining, and then what are the common issues which are encountered when the dissimilar metals are joined, especially using the fusion welding processes. And then what are the strategies to develop the dissimilar metal joints to reduce the issues related with the dissimilar metal joining or welding. And then we will talk at length about the dissimilar steel welding, that is austenitic stainless steel and ferritic martensitic steel. Okay. And then we will be taking up the another dissimilar metal combination joining related case, that is the steel aluminum welding. So, and then thereafter we will be taking up one case study where failure analysis of the dissimilar steel joints have been undertaken, and that will include like failure analysis observation and the findings. So, dissimilar metal joining is little complex. Why? Because it is really difficult, because the two metals to be joined are different. Like say there is a metal A and B. These two metals A and B may be significantly different in terms of the mechanical properties, in terms of the physical properties, chemical properties, and even metallurgical properties. Okay. So, because of these differences, when the welding is carried out either using solid state joining approaches or fusion welding processes, lot of problems are encountered. So, if we talk about the physical properties and the relevant physical properties that lead to the difficulties related with the dissimilar metal joining, these include like difference in melting temperature. It's possible like A is having 1600 degree centigrade melting point, but B is having just 600, like typically in case of the say steels, or steels will be having like around 1400 and aluminum around 600 degree centigrade. So, there can be lot of large difference. Similarly, thermal conductivity, A may be very high thermal conductivity and B may be of very low in thermal conductivity. So, that will be affecting if the heat is applied at the center, then the distribution of the heat or heat dissipation to the base metal will be different. Likewise, when the thermal expansion coefficient alpha is different, then it will be causing the differential expansion and contraction during the welding, and that in turn poses a lot of residual stresses in one of the metals that is having the lower thermal expansion coefficient, and the presence of the tensile residual stresses in one of the metal which is experiencing these tensile residual stresses, that will be showing greater tendency for cracking, or like in the solid state joining also, when the heat is applied and like say A and B, and here there is no fusion, only the joint at the interface is being formed. So, in those cases presence of tensile stresses at the interface also leads to the cracking. Okay. So, in that case the cracking at the center is observed. So, the point is, when the two different metals are joined or welded, that leads to the lot of problems due to the difference in physical properties. Say the difference in physical properties in terms of solidification temperature range in the fusion welding causes the solidification cracking. Okay. Metallurgical incompatibility is another major issue, especially when the metals are completely different, like say the metal like aluminum joined with the steel. So, they are not really compatible with each other because of the limited or nil solubility. So, this kind of incompatibility leads to the formation of aluminum AXFEY kind of the intermetallic compound. So, all combinations like say copper, iron or copper, aluminum, such combinations where the systems are incompatible, when they are brought in contact with each other, that will be leading to the undesirable intermetallic compounds which will be hard, brittle, leading to the reduced tensile strength and ductility. Okay. Strengthening mechanisms of the metal is another issue, because like when the same treatment is given to both the systems, one may be showing one may be strengthened by one approach, another may be by another approach, then that will be leading to the different response to the heat treatment when the same amount of heat is applied to both the metals, like say A and B. So, these can be strengthened by say precipitation hardening, grain refinement, solid solution strengthening, work hardening, transformation hardening, or dispersion hardening. Okay. So, if there are two different metals, it is possible like they are strengthened by the different approaches. When the heat is applied, obviously the response of the two metals will be completely different. That is why metallurgical incompatibility also poses a lot of challenges in the development of the dissimilar metal joints. The difference in mechanical properties, especially in terms of the yield strength and percentage elongation, that is ductility. Okay. These two are extremely important in dissimilar metal joining, especially using the solid state joining processes. So, like the friction welding or friction ester welding or friction ester spot welding. So, in those cases where the joint is developed in the solid state through the controlled plastic deformation, okay, there the yield strength and ductility is important. But what happens when we have two different metals A and B, one is of 700 MPa yield strength, another is 400 MPa, then they flow differently while the solid state joint is being developed. It is possible like one is showing the 20% ductility, another is just 5%. So, that will show the greater tendency of cracking or limited deformation. So, the difference in mechanical property of the two metals which are being joined, they pose challenges, especially when the solid state joining methods are used. Okay. Then chemical properties are like chemical properties includes like composition and the affinity with the gases. So, the different metals which are being joined by fusion building processes, they may respond differently to the gases, and when they mix up with each other, the response of the molten weld metal after solidification, that may be completely different. Okay. So, here we have A and B. If they are say A, when is added in B, it can lead to the a completely different kind of the response. Okay. So, which may lead to the extremely undesirable characteristics of the fusion weld joints when such kind of the chemically incompatible material systems are joined by the fusion welding. Okay. So, as a result of the difference in physical properties, metallurgical properties and mechanical properties and chemical properties, what we commonly come across is a symmetric weld. Weld is usually not symmetric. So, because of the difference in physical properties, the weld is skewed more one side as compared to the other side. So, the weld is not symmetric. Otherwise, the weld should have been symmetric, where the equal amount of the molten metal and after solidification weld metal is being produced about the weld center line. Okay. So, this asymmetry is usually present due to the difference in physical properties. Then it is possible like one is getting hardened and another is getting softened because of the difference in the way by which it is those metals are getting strengthened. Then unmixed zone formation due to the difference in the chemical characteristics, the difference in surface tension, difference in viscosity, difference in flow characteristics. In the molten weld metal, what happens, sometimes unmixed zones are formed, and these zones can be formed in both the sides of the fusion boundary. So, at the center we have weld metal, while next to the fusion boundary there are unmixed zone formation, which means the concentration of certain elements is excessively high, while the presence of those elements is deficient at other locations. Okay. So, unmixed zone formation means chemical heterogeneity, means heterogeneity in terms of the mechanical properties as well. So, then residual stress development and distortion tendency. The greater the difference in thermal expansion coefficient of the two metals being joined, greater will be the residual stress formation at the joint interface and distortion tendency accordingly. And the metallurgical incompatibility leads to the formation of the hard and brittle intermetallic compounds, which in presence of the tensile residual stresses will be leading to the cracking. Okay. So, this is what I was talking about. The different metals are strengthened by the different approaches. So, these are the common approaches: work hardening, precipitation hardening, grain refinement and transformation hardening. These highlighted ones indicate that they are affected by the heat when the joint is developed, but the effect of heat is not much when the metal is strengthened by the dispersion and solid solution strengthened metal. The point here is, it's possible like metal A is strengthened by the work hardening and grain refinement, while B is hardened by the precipitation and transformation hardening. So, the response of the heat treatment will be completely different because of the difference in the mechanism through which they are getting strengthened or they are hardened. So, this is what further demonstrates like what major difference in the chemical properties. Chemical properties affects the surface tension and viscosity of the molten metal, okay, and melting temperature, difference in composition, difference in the metals affect the melting temperature, then difference in thermal conductivity. So, difference in composition and thermal conductivity, these two factors especially affect the weld bead geometry, weld cross section. So, here we can see metal A, the weld zone is more skewed towards the A as compared to that of the B because of the increased possibility of flow of the molten metal towards the metal A, because metal B would have been showing the lower surface tension, okay, ST is low on the B side and it was high, that is why it was flowing in this side, and that is why most of the heat got transported towards the A and that resulted in a greater melting. Okay. And likewise, it is possible like thermal conductivity of metal is more, so more heat it is taking and the heat transferred towards the B is limited. So, there is another side of this that because of the difference in thermal conductivity, metal A is getting more heat as compared to the dissipation of heat towards the B. So, it leads to the difference in the heat affected zone width. HAZ width is more in one side of the metal as compared to the another side. So, because of this difference in thermal conductivity and chemical composition, this leads to the asymmetric weld and the different widths of the heat affected zone. Okay. And these in turn will be leading to the uncontrolled dilution and differential penetration on the two sides and the metallurgical issues. Okay. So, what we can do to deal with the challenges related to the difference in mechanical, physical, chemical and metallurgical properties of the two different metals which are to be joined. Okay. Say this slide demonstrates the effect of thermal conductivity. What happens when thermal conductivity is extremely high? Means the heat is heat is dissipated to a greater extent to the base metal, and that in turn limits the size of the weld pool which is produced. Okay. And the width of heat affected zone in this case is wider. So, a smaller weld cross section and wider heat affected zone. Reverse happens when the thermal conductivity of the metals being joined is limited. In that case, heat dissipation to the base metal will be limited. So, the HAZ will also be limited. Okay. On the other hand, most of the heat will be used for melting or to facilitate the fusion of the base metals, and that in turn will be leading to the increased cross section, large cross section of the weld and the narrow heat affected zone. Further, if we see, if the thermal conductivities of the two metals are different, like one side it is less and another side it is more, then most of the heat will be dissipated towards the high K side, and therefore, weld pool will be skewed towards the high thermal conductivity metal as compared to that of the low thermal conductivity, and this in turn will be leading to the asymmetric weld. Okay. So, what are the strategies that can be used for developing the weld joints of the dissimilar metals? One is like if we are joining A with B, wherein A and B are not directly compatible with each other. So, what we try to use? We try to use the C as a filler which is compatible to both. Okay. For example, there are a lot of examples of this kind where like say the iron and the aluminum, two are directly not compatible with each other. So, but if the nickel is used, then it will be compatible with both, and that will facilitate the joining without much of the issues. This is one of the approach where compatible filler metal is used. The second approach, let us isolate A and B from each other. So, we use the cladding layers like this. Cladding layer of compatible metals help to isolate A and B from each other, and then use a filler of any suitable material. So, suitable cladding or buttering layer is deposited. So, there is one buttering layer deposited on the metal B and another buttering layer deposited on the metal A, and in this case it is ensured that both these buttering layers are compatible with the filler metal C. Okay, so that later on the metallurgical issues are not encountered. Now, so here this is the second approach where the incompatibility between metal A and B is very high, and therefore it needs the buttering layers to isolate them from each other, followed by filling the gap using the suitable compatible third kind of metal which is compatible with both kind of the buttering layers. There is a third approach where metal A and B are really incompatible with each other. So, we bring the third member. This is not the filler metal, but this is a third member or third component which is brought in between, made of the C metal, which is compatible with both A and B. So, this is called transition joint where, or trimetallic joint. So, there is a metal A, metal B and metal C is brought in between A and B, and then two different weld joints are made between A and C and B and C. Okay. So, this is a typical example where AISI 316 austenitic stainless steel is being welded with the ferritic martensitic steel with the help of where in trimetallic means the trimetallic components, third component is of Ly 800, and then these two are welded using the suitable compatible filler metal. So, this is called the trimetallic weld joint approach. So, trimetallic weld joint approach. Here we are using the buttering or the cladding, and here simply we are using the filler metal which is compatible to both these metals. Okay, now we'll be talking about the dissimilar metal joining where the ferritic to ferritic steel welding is commonly used in these components related to the thermal power plants. Okay, ferritic steel to the austenitic stainless steel is used in these thermal power plants like steam generator and steam pipings, and but because the thermal power plants will be working in on and off mode, means there will be heating and cooling. So, because of this heating and cooling cycle that is imposed, what happens if the components which are connected with each other having a difference in thermal expansion coefficient, then they will be causing the residual stresses and eventually thermal fatigue, which will be leading to the cracking and the fracture. Okay. Another problem that is encountered is the carbon migration, especially in such kind of the dissimilar steels. Say ASS is of very low carbon in terms of carbon content 0.05, but the our P90, our carbon steels, other alloy steels or ferritic martensitic steels say having 0.2% carbon. So, because of the good affinity of the carbon and because of the compositional difference, when the weld joint is made directly, carbon starts diffusing from the high carbon zone to the low carbon zone. So, when carbon migrates towards the ASS side, the carbon enrichment takes place. This carbon enrichment, say once if it reaches 0.07 or 0.1, then there is a huge tendency, there will be huge tendency for formation of the chromium carbide, that will be leading to the sensitization. Sensitization means reduced corrosion resistance of the heat affected zone. So, about that problem we have talked in the previous presentation, that the loss of the corrosion resistance of the austenitic stainless steel weld joint due to the formation of the chromium carbide due to the inappropriate welding conditions, that leads to the sensitization. Okay. But in this case, the carbon is getting migrated from high carbon zone to the low carbon zone if the welding is not done properly. Okay. So, how to deal with these challenges? Okay. So, say P91 is steel having the thermal expansion coefficient of the 12.6 units on, and the P22 is having thermal expansion coefficient of the 12 units. This is another ferritic martensitic steel. These are chromium molybdenum steels basically. On the other hand, we have P91 12.6 and where and 316 having the 18. So, here the difference when the P91 is welded with the 316, then the difference is of about 6 units. Okay, the 12.6 in one side and 18.8 on the other side. So, when such kind of the combination is subjected to the thermal cyclic heating and cooling, then that will be leading to the lot of issues including fatigue cracks. Okay. So, how to deal with this problem? So, here like the P91 is one on one side and 316 on the other side, and in between the trimetallic weld, the transition piece is added in case of the trimetallic joints of the LY 800 having the 17 thermal expansion coefficient. Okay, this is one example wherein we will try to demonstrate how the properties get affected when P91 is welded with the 316 directly or with the use of suitable compatible filler metal. So, say TIG welding was carried out, TIG welding was used for joining of the fusion welding of the dissimilar combination of the P91 and 316, and in this case say this is one case where no filler was used, and then the case when so this is showing the corresponding cross section of the weld joint T16 and P91. Then Inco LY 800 was used as a filler, or that is a means interlayer, and then P91 and 316, and then Inconel of Inco 800 and Inconel 600 when it was used as an interlayer, and then cross section was studied. So, what we found, like how the things get affected when these joints were subjected to the toughness test, what found that completely brittle fracture was observed with the joint when there was no interlayer, and it showed the brittle fracture with the toughness of the 33 without interlayer. But when the interlayer of the Incoli of 800 was used, it increased to the 93, and with the Inconel 600 it increased to the 98, and also the proportion of the dimple fracture also increased in the fracture surface. So, this indicates that use of the suitable filler in dissimilar steel combinations can help in enhancing the properties, especially, which is important. This is another approach where the dissimilar metal combination is welded using the functionally graded weld metal. Okay. So, in this case there is one direct metal joining where P91 and 316 weld joints are made, and this is the corresponding joint. One single weld is made and the joint is obtained with 316 and P91. When the functionally graded weld joint is made using the TIG welding approach, like activated TIG welding approach here. So, P91 then 316, P91 316, P91 316. So, a suitable combination was identified, and then three different passes were given. In one pass 316 and P91 one side was welded, then second pass was made, and then third pass was made. So, using three different passes, these layers which were stacked in a proper and particular order were subjected to the heat and for the welding, and then at the end we got the weld joint, and cross section of the weld joint showed a proper gradation in terms of the hardness and composition. So, what it shows how the composition changed, and that is in turn also resulted the gradation in terms of the thermal expansion coefficient. Okay, and that in summarily also we can see the gradation in terms of the chromium and nickel equivalent in the such kind of the dissimilar steel weld joint. So, this analysis was carried out using EPMA. So, conventional TIG welding shows the sharp transition actually in terms of the composition of the weld metal, but this transition was stepwise in three different passes which were obtained in functionally graded weld joints, and that also was observed in case of the conventional as well as the functionally graded weld joints. So, in case of the functionally graded weld joints, if you see chromium equivalent and nickel equivalent values can be seen here, like say for 316 it is 18.9 and 11.6, 17.9, 10.8, 14.1, 7.1, 11.9 and 4.9, and 9.6 and 3.5. The point here is there is a continuous gradual change in the chromium and nickel equivalent values. It is not direct change like 18.9, then 13.7 and 9.6. On the other hand, nickel equivalent here it is changing from 11.6, 6.6 and 3.5. So, there is just one step, otherwise here we have got like say 3 steps. So, that is indicating more effective grading as far as the compositional variation is concerned, and that is expected to improve the properties significantly. Now, this is another combination actually wherein we will be talking about the aluminum and steel joining. Okay. So, we know that efforts are being made in automotive sector a lot for reducing the gaseous emissions and increase the fuel efficiency. So, efforts are made to reduce the weight. So, but it is not happening actually to for the sake of better comfort and the safety, the systems are getting of the more weight as compared to the older ones. So, if you see the old car weighing around 778 kg, but those new ones are weighing 800 kg. So, lot of efforts are being made in order to reduce the weight, like say lot of advanced steels are being used for fabricating the components in automotive sectors. At the same time, non-ferrous metals are also being used like magnesium, aluminum, even the plastics, polymer composites are being used so that the weight of the automobiles can be reduced to enhance the thermal efficiency. Fuel economy, emissions can be reduced, fuel economy can be enhanced. So, efforts are basically targeted to reduce the weight so as to enhance the fuel economy and reduce the emissions, and therefore lot of developments are taking place by making the high strength to weight ratio metals. Another approach is combining the variety of metals as per the need of the application of a particular component. So, use of the hybrid structures. So, in this connection only it is required, we cannot make everything of a steel or polymer, but just for the sake of very high strength or for lower weight, we need to take a judicious call about which component can be made of which material, and then they need to be connected and joined together. So, there are a lot of applications where in automotive sector where it is required to join the steels with the aluminum. Okay. So, but joining of the steels with the aluminum is not so easy. Why? Because the large difference in their melting temperature, like it can range from this 463 to 671, while the steels having 1425 to 1540. Okay. Thermal conductivity also very significantly very high in terms of thermal aluminum is very high in terms of thermal conductivity, and also electrical resistivity is very low. Thermal expansion coefficient is very high as compared to the steel. Diffusion coefficient, if we see diffusion coefficient is low as like say aluminum in iron is this much and iron in aluminum is this much. So, this is very high. Solubility of aluminum in iron is almost negligible. Okay, and the ductility is high, it is moderate in case of the steels, and yield strength is also moderate, like say 200 400 MPa, and in case of steels it is too wide range depending upon the steel compositions and the condition of the steels. What happens when the aluminum is subjected to fusion welding with the steels? Okay. So, the problem or the challenges imposed in such kind of dissimilar metal joining include like large difference in the melting point and thermal expansion coefficient. So, because of this it is preferred to do the brazing so that the related issues can be reduced. Due to the metallurgical incompatibility between the aluminum and iron, it causes a lot of the IMC formation which promotes cracking. Okay. Large difference in thermal expansion coefficient causes high residual stresses at the interface especially. And then large difference in mechanical properties in terms of yield strength and ductility, this leads to the defective weld in the solid state joints. So, if we see the typical steel, okay, and aluminum weld joints at the interface, there is a thin layer of the IMC which is formed, and this thickness of this layer actually increases with the increase of the heat that is being supplied. So, this heat can be supplied in number of ways depending on the process which is being used. Like say in fusion welding, if the heat is amount of heat is increased, then IMC layer thickness and amount of the IMC that is being formed, that also increases. But this layer is extremely thin when the solid state welding is carried out because the limited use of the heat input. Okay. So, when the IMCs are formed, it is a really problematic thing. Why? Because when the variety of the aluminum iron IMCs are formed, so when the aluminum is less in the IMC, you see that hardness is limited. Okay. Hardness is 344 to 360. But when the aluminum in iron is more, then this keeps on increasing the hardness of IMCs which is formed. Okay. So, this high hardness of the IMC, we know that martensite is of the hardness 500 to 700 or 800 HV. But on the other hand, if we see the IMCs which are being formed, they are extremely hard and brittle with the high in aluminum. So, aluminum iron IMCs which are rich in aluminum, they offer extremely high hardness and brittleness. So, it is still favorable, not that harmful, to have the aluminum iron IMCs with the low aluminum content. There is another way, let us modify the characteristic or composition of the aluminum iron IMC using the suitable zinc, silver, silicon or something else which can modify the characteristics. So, instead of preferring to go for the fusion welding, in fusion welding there is a huge amount of the IMC formation that makes the weld very brittle and almost immediate cracking is observed. So, steel and aluminum and in between obviously heat affected zone both the sides, and in between very hard, brittle, low strength, low ductility IMC is formed at the center. Aluminum is softened because of its reversion and grain growth. On the other hand, steel is hardened because of the martensitic transformation. So, in fusion welding this heat is maximum. So, maximum damage in that way. So, the idea here is to use the solid state joining so that the issues, related issues can be minimized. So, let us use the FSW or stationary shoulder FSW. Okay. So, when the FSW is used, the amount of the IMC layer being formed is reduced, HAZ is also reduced. So, this offers the medium heat input, low strength, low ductility nugget is formed with the thin IMC layer and HAZ width is also minimized. So, the zones of the heat affected zones which are formed both the sides, that is minimized, and severity of the heat on these HAZ is also reduced. It will be the best way if we use the stationary shoulder FSW. So, in this case only the pin rotates and the shoulder does not rotate, shoulder remains stationary in case of the stationary shoulder FSW. So, the HAZ is found just in one side and the IMC layer is also very negligible and the good strength and ductility is observed, especially due to the good heat you see minimum net heat input for developing the sound joint. So, as I said, modifying the characteristics of the IMC is one of the ways which can be done through the proper control of thermal cycle or by suitable controlled alloying. So, control of thermal cycle basically involves use of suitable welding process or suitable joining process, and on the other hand controlled alloying includes like using the suitable elements that can modify the characteristic of the IMC like zinc. Okay. So, how the FSW of the aluminum and steel weld joints is carried out, that is what we can see. Aluminum and steel weld joints are developed by putting the tool pin not at the center, but tool pin just touches the surface of the steel and mostly it penetrates to the aluminum, and then rotary movement leads to the development of the joint at the interface. There is another approach where the brazing or the spot welding is carried out of the dissimilar like say metals like steel and aluminum. So, in this case higher conductivity aluminum, low melting point aluminum in spot welding leads to the greater amount of the heat affected zone formation on the aluminum side and more nugget is on the aluminum side, and but IMC is formed on the steel side because of this interaction, and then little heat affected zone will also be formed on the steel side due to the limited conductivity. Okay. So, brazing is another way where the compatible material is used between the two metals, and but that will be leading to the IMCs and the both the ends. Okay, and that in turn will be leading to the like reasonably good joints. Okay, when such kind of the dissimilar joints subjected to the tensile stresses, this is what we can see. Stress distribution also changes across the section. We will talk about one case study on the failure analysis of the component made of the austenitic stainless steel and carbon steel weld joints. Okay. So, a structural member of thermal power plant made of the AISI 304 and AISI 1030. The joint failed prematurely within 1 year of the service, and so investigation was carried out, and it suggested that 310 and 1030 steel compositions were there as per specification, design was as per specification, and welding was carried out using GMAW without cladding or buttering, and the filler was used of AISI 310. So, visual examination of the failed component shows corrosion related pits and cavities in the heat affected zone away from the fusion boundary, that is indicating the sensitization. Okay. Mechanical properties were as specified. At the same time, grain microstructure of the weld joint and heat affected zone shows fine grained austenite and the coarse grained HZ, but with the unmixed zone formed on the austenitic stainless steel, that is the enrichment of the carbon and other alloying elements near the fusion boundary on the austenitic steel side. NDT showed no defect whatsoever, normal operations, no maintenance requirement, and the XRD study shows the sensitization, means the chromium carbide formation, and that led to the selective depletion from the grain boundaries in the heat affected zone. And the SAM you see, stereoscopy suggested the corrosion in the heat affected zone, and the comparison of the failed component with the new component showed that the cladded weld joint with the similar filler in the new was there. So, cladding was used in the new component while it was missing in the failed one. So, that facilitated the migration of the carbon from the carbon steel side towards the ASS side, and that resulted in the sensitization, and which eventually led to the pitting and the cavities in the heat affected zone in corrosive environment. Okay. So, all above suggested that the failure by sensitization due to the absence of the cladding layer which should have been there, and it was a deviation from the recommended WPS. So, now I will summarize this presentation. In this presentation, basically I have talked about the fundamentals associated with the dissimilar metal joining, and what are the common problems which are imposed during the dissimilar metal joining, and what strategies we can follow for developing the sound dissimilar metal joints. And we have taken up one case study on the dissimilar austenitic stainless steel and carbon steel weld joints for better understanding and application of the subject. Thank you for your attention.